Okay guys, so let's get straight to the limit. We're supposed to evaluate the limit as n goes to infinity of the square of the nth root of a plus the nth root of b all over 2 and all to the power of n. So as you can see, as n is approaching infinity, the nth root of something, which is the 1 over nth power of that something, is going to approach this something to the power of a 0, which is 1. And so this a and this b under those roots here and here are going to approach each one. Yeah, and so this entire numerator there is going to approach a 2, and that means that this entire thing under this nth power, yeah, so this parenthesized expression here is going to approach 2 over 2, which is a 1. And so this entire thing is going to be actually approaching a situation of 1 to the power of infinity, which is an undefined situation. So we have to, well, deal with it a little bit more creatively. So, well, whenever we have a limit where we're just kind of raising a 1 to the power of infinity, what we can do is use a nice, actually a lovely identity that saved my ass, you know, and the ass of a lot of Calc 2 students throughout their lives, which is that the natural log of a limit is the same as the limit of a natural log of something. Yeah, so what we can do is just first of all denote this limit I want to evaluate as some kind of an L. Yes, I would like to set my L equal to the limit as n approaches infinity of this nth root of a plus that nth root of b all over 2 and all to the power of n. And now we can just go on and take the natural log of both sides. And so what I'm gonna get then is the natural log of L being equal to the natural log of this entire limit, which is, well, the limit of the natural log of the stem that is inside of this limit. So the limit as n goes to infinity of, well, the natural log of this entire expression. I'm not gonna be writing down again, I'm just gonna copy it. Yeah, so I'm lazy as hell. Okay, so this thing right there. But now what we can do is just nicely use the properties of logarithms of the laws governing those. And so we can just take this n from the exponent there, oh, not quite here, and just drag it in front of the logarithm, so we don't have it in the exponent inside of the logarithm. Yeah, and I also should have put under parentheses. Now it's better. Okay, so now what we can do is write this entire thing as a natural log of L being equal to the limit as n goes to infinity of n multiplied by the natural log of the square root, of the nth root of a plus the nth root of b all over a 2. Lovely. But now, well, I'm gonna thinking. We're not getting anywhere close to this solution here because we are, multiplying by an infinity there. We are getting a natural log of a 1 there, so it's gonna be a infinity times 0, and well, I don't really know what to do with this kind of a situation. I mean, I can't use the L'Hopital's rule or anything because I'm not dividing anything by anything. I'm just multiplying stuff. I don't like it. So, well, it would be a nice idea to get some kind of variable, let's say this n, into the denominator, so I would be able to take the derivative with respect to the variable at hand and just, use the L'Hopital's rule or something. How can I do that? Well, actually, I could apply a nice change of variables here. I mean, if I were to change my n to some kind of x in such a way that n will be equal to 1 over that x, and also then the nth root of a would be equal to a to the power of x, and well, the nth root of b would be equal to b to the power of x. Well then, if I wanted my n to be approaching positive infinity, what will my x be approaching in order to 1 over x to be approaching positive infinity? Well, I shouldn't have put those lines here. Now it's better. And for my lines of limitation. Yeah, we have that as n is approaches infinity, so 1 over x is approaching infinity. We get that x has to be approaching 0 from the positive x direction from the above. Now, so we're going to rewrite our entire limit while applying this change of variables here as the natural log of our original limit being equal to the limit as our new variable x approaches 0 from above of, well, this n will magically change into 1 over x, so I will just write it as such now. This natural log of all of that stuff doesn't really change. I'm just gonna write it as the difference of the natural log of the sum of those roots and the natural log of the two, just so I'm some kind of more convenient with dealing with all of that things later after using L'Hopital's, yeah? So it's gonna be the natural log of, well, this nth root of a will become a to the x, just as well as the nth root of b is gonna become b to the x, and then this negative natural log of 2. So, well, yeah, we did it. We have a 0 over 0 situation. As you can see, this natural log of a to the x and b to the x is going to be the natural log of a 2 as our x is approaching 0, because anything to the 0 is 0, and then what we get is this negative natural log of 2, and so those two are going to cancel each other out. I'm going to get a 0 in the numerator, and also this x is approaching 0 in the denominator, so that's a perfect place to use the L'Hopital's rule. So you can just go on and take the derivative of all that stuff with respect to x in the numerator and the denominator, so our natural log of the original limit is going to be equal to the limit as x approaches 0 from above of, and now the derivative of this x in the numerator is just going to become a 1, so I'm not even writing it down. This derivative of the natural log of 2 is also be, not also, but it's going to be 0 for sure, so we're only going to focus on the derivative of this natural log of the sum of a to the x and b to the x. That's going to be, well, in the denominator, by the chain rule, we're going to get a to the x plus b to the x, and now we have to multiply it through by the derivative of this stuff inside of the logarithm, which is a to the power of x ln of a plus b to the power of x ln of b. But this stuff, well, we can deal with without a problem, as x is approaching 0, a to the x is going to be approaching, not a 0, a 1, b to the x is going to also be approaching a 1, and so we can just apply it here, here, and here. So, well, this entire thing is actually going to be approaching just the average of those ln of a and ln of b, but you can once again use the laws governing logarithms in order to write this thing as the natural log of a times b all over 2, which is the same thing as the natural log of the square root of the product of a and b. But we'll notice that this is only the natural log of our original limit, and so we can write that our original limit L is equal to e to the power of the natural log of square root of ab, which is just the square root of ab. Oh, I didn't underline it entirely. Obviously. So let's go all the way back and say once again what did we do here. So what we did is, first of all, we wrote this entire expression in terms of natural log, stuff like this, just in order to get rid of that 1 to the power of infinity situation that we had at the very beginning. Then what we did is we changed the variables such that we could use the L'Hopital's rule, yes, so we changed our n, I wanted to use some different color, so I'm going to use orange here, so n into 1 over x, so that x then became our denominator, and we could use the L'Hopital's rule in order to evaluate this limit that was the natural log of the original limit, and so we then got that our original limit is equal to the square root of a and b. I really hope you guys enjoyed this video. If you did, well, like and subscribe to my channel, because I'm posting every single day, so there's a lot of stuff to miss out on, and well, see you next one. Bye.